Hi everybody. In today's video we're going to discuss electric fields and how to calculate electric forces using something called Coulomb's law. So here is a nice analogy that works for a lot of people. You are already used to fields. The idea is that we've been discussing the weight of objects and the force of gravity on objects. Well, what's the formula for the weight of a massive object? That is W equals mg, where W is the weight, m is the mass, and little g is the gravitational field strength. Now, before, we simply called it the acceleration due to gravity. Well, you could, if you wanted to, call the electric field the acceleration due to electricity or electric charge. Well, technically it's the acceleration on the electric charge, but it's the same type of idea. The idea is that this acceleration due to gravity, which i.e. the gravitational field strength, tells you how much force is going to act per unit mass. So the units of the gravitational field strength, we're used to those units being meters per square second. But wait a second, look at our equation. F equals mg, or W equals mg. You could also say that, well, that means that newtons is equal to kilograms times the units for g. So therefore the units for g must be newtons per kilogram. That's the same thing as a meter per square second, but the point in stating the units this new way is that if you tell me how many kilograms of mass I have in the gravitational field, I will tell you how many newtons of force are acting on this, the number of newtons per kilogram. Well, guess what? It works exactly the same way with the electric field strength. If you tell me the electric field strength, I'll tell you the amount of force that a certain amount of charge will feel or will experience due to this electric field. The equation is F equals QE. So just as W equals mg, or force of gravity equals mass times gravitational field strength, well, here we have force of the electric field is equal to charge times the electric field strength. That reminds us of the fact that forces due to gravity are caused by mass in a gravitational field, and forces due to electricity are caused by charge in an electric field. Now, one thing that we need to get straight first of all is, as far as we know, there is no fundamental unit of mass, so to speak. There, at least not anything that you could really count on a scale that you would really be able to measure. There is such a unit for charge, though. There is a smallest possible elementary unit of charge. That is the magnitude of the electron's charge. The elementary charge is about 1.6 times 10 to the minus 19 coulombs. Remember, the electron's charge is negative, so the charge of the electron is negative E. Do not confuse the symbol E for the electron. The symbol E here stands for elementary charge. So this is the smallest possible unit of electric charge, at least that you would really be able to isolate. So some of you who know a little bit of fundamental physics might think about, well, what about the Planck mass or something like that? Isn't that a fundamental unit of mass? Well, that's a bit different. The Planck mass, ironically, is actually the largest possible mass that you can have for a potential subatomic particle. And it's also the smallest mass that you can have for a black hole. But you can have actual masses of things that are a lot smaller than the Planck mass. For example, the electron's mass is about 9.1 times 10 to the minus 31 kilograms. And the mass of a neutrino is probably at least 1,000 times less than that, if we can actually measure the mass of a neutrino, which is very, very hard. But in any case, there isn't a smallest possible unit of mass as far as we can tell at this point, but there is a smallest possible unit of charge that you could actually isolate, and that is the magnitude of the electron's charge, which is the same as the magnitude of the proton's charge. So let's consider a quick example. What would be the force that a carbon-12 nucleus would feel in an electric field of 2.5 times 10 to the 6th newtons per coulomb? Well, let's see now. A carbon-12 nucleus has 6 protons and 6 neutrons, but the only things that actually have charge are the protons, because we're saying it's a nucleus, which means all of the electrons have been kicked away from this previous carbon-12 atom. So all that's left is the nucleus, but it's the protons that give you the charge. So we have 6 elementary charges there. So writing out our givens, we have Q is equal to 6e. And in this case, I actually multiplied that out ahead of time in my givens. I did not need to, but I decided to. And we also have our electric field strength. If I had not multiplied this out, I would simply say now that F is equal to N little e times big E, where N is the elementary charge, or the number of elementary charges in this case, which is 6. But again, I decided to multiply it out. So now we just have F equals little q times big E. Multiplying out gives us 2.4 times 10 to the minus 12 newtons, or 2.4 piconewtons for those of you who love Greek prefixes. Now, if we wanted to figure out the acceleration that such a thing would feel, then you could actually do that because we know the mass of a carbon-12 nucleus. So let's do that. Calculate the acceleration that a carbon-12 nucleus would undergo in that same electric field that we just dealt with. Well, we know Newton's second law. Of course we do. F equals ma. Force equals mass times acceleration. It's only one object. It's only feeling one force, the electric force. So what about that mass? Well, the mass of a carbon-12 nucleus is 12 AMUs. In fact, I probably should correct this slightly because there was a recent redefinition of the atomic mass unit that occurred, I believe, on May 20th of the year 2019, and it is no longer defined to be exactly 1/12 the mass of a carbon-12 nucleus. It's actually defined to be exactly like 1.6605 something 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 times 10 to the minus 27 kilograms. And that is the new definition. So if you want the exact definition and the exact number, look it up on Wikipedia. But in any case, for our purposes, this is still correct to 6 significant figures, and we certainly don't need that many in this case. So I plugged in the atomic mass the atomic mass unit right here to give us the mass of a carbon-12 nucleus. And now, since we already calculated that force in the previous example, then solving for the acceleration that such a nucleus would experience, we get 1.2 times 10 to the 14 meters per square second. And if you obtained a slightly different value in the non-rounded result, that's because you might have used a less precise calculation. You might not have plugged in the full value for the atomic mass unit, or you might not have plugged in the full value for the force that we determined in the last problem. But I kept all of my decimal places, which is what you should do too. So hopefully, at least upon the rounded result, you got 1.2 times 10 to the 14 meters per square second. You might wonder, it's like, well, that's a really big number. I know that the speed of light is 3 times 10 to the 8 meters per second, but keep in mind, velocities and accelerations are completely different things. So it is perfectly okay to have a really big acceleration for something as long as that acceleration is not acting for too long of a time. And remember, it's not possible for an object to be observed to move faster than the speed of light. But a very big acceleration like this is perfectly fine. Now let's move on to Coulomb's law. How do we actually calculate electric forces between charged particles? So it is an experimental fact that if you take two charges and you move them closer to each other, you get a bigger force. In fact, it is also an experimental fact that, and also for that matter a mathematical fact, that this force is inversely proportional to the square of the distance between the charged particles. So that inverse square law, where have we heard that before? Thinking back, that's Newton's law of universal gravitation as well. It works for mass, it also works for charge. So here is the law. The force is proportional to the product of the charges and inversely proportional to the square of the distance between the centers of the charges. And again, this is just like Newton's law of universal gravitation. In Newton's law of universal gravitation, the gravitational force between two massive objects is proportional to the product of the masses and inversely proportional to the square of the distance between the centers of the masses. Well, same thing for charges, just replace the masses with charges. But notice the proportionality constant. the proportionality symbol here. The constant that turns this into an actual equality is different for Coulomb's law than it is for Newton's law of universal gravitation. After all, that constant with Newton's law of universal gravitation tells you something about how strong the gravitational force is at a fundamental level. Here, the proportionality constant tells us how strong electric forces are on a fundamental level. So the proportionality constant is usually given by the symbol lowercase k, although sometimes k is written in this funny way right here, 1 over 4 pi epsilon naught, where epsilon naught is a different constant. The reason that's often done is because this constant epsilon naught often shows up in somewhat more advanced electric field calculations, and it's very useful for physics students when they're doing stuff like that. But they are related by this relationship, the fact that k is 1 over 4 pi epsilon naught. Epsilon naught actually has a defined value nowadays. It's equal to, well, it's given such that 1 over epsilon naught times mu naught, which is another constant of nature, where both epsilon naught and mu naught are in the denominator, is equal to the speed of light squared. But in any case, this value k is what we care about, and for our purposes, it's about 9 times 10 to the 9 SI units. Well, what should our SI units be? Yeah, I know you see them right here, but we need to actually make sense of these units. If you can make sense of the units, then you don't have to really think too hard about what the units are. Well, let's see now. Here's our force equation. We have force is equal to a constant times the product of charges divided by the square of the distance between the centers of the charges. Well, we know the units of force. Those are newtons. Remember, the units on one side of an equation must be equal to the units on the other side of the equation. Otherwise, it's not an equation. It's simply a pile of rubbish. But we have units of newtons on the left side of this equation, and on the right side, well, let's see, our coulombs are units of charge, as we mentioned last time. So we have 2 powers of charge in the numerator, so that's going to be a coulombs squared. We have units of distance squared in the denominator, so we have coulombs squared in the numerator, meters squared in the denominator, and we want to magically turn this into newtons. Well, that means that our proportionality constant must cancel these meters squared in the denominator. So there's where our meters squared in the numerator comes in. It must cancel the Coulomb squared in the numerator. That's where the Coulomb squared in the denominator comes in. And we've canceled everything. We need units of force, which are newtons, so that's where this newtons comes in. So that's why these units are the way they are. In fact, you might remember back from Newton's law of universal gravitation that the units of Newton's gravitational constant are Newton meters squared per kilogram squared. Well, here we're dealing with charge, so it's Newton meters squared per Coulomb squared. Now, let's actually deal with the equation itself. We've already talked about how familiar it looks with Newton's law of universal gravitation. In fact, there is a theorem that relates these types of equations between gravitational interactions and electric interactions. Now, you do need to be careful with units. We're always going to be dealing with SI units. However, a coulomb, as we've mentioned, is a very large amount of charge. Typical everyday charges are in the order of microcoulombs or nanocoulombs. Well, micro is 10 to the minus 6th and nano is 10 to the minus 9. So whenever you're dealing with something like that, make sure that you convert into SI units before you start. Now, here is the technical version of how you deal with these forces when you have a bunch of charges. Like, let's say you have, say, 4 charges randomly oriented in space, and you need to figure out the force on one of the charges due to the other 3. Well, the net force, just as it was when we were dealing with free body diagrams, is equal to the sum of the individual force vectors. And in this case, we are using the vector nature of the force. So how does that work? Well, the magnitude of each of the forces is given by Coulomb's law. So let's say that the charge we're interested in is just lowercase q, and each of the other charges are q1, q2, q3, etc. Well, the magnitudes are each given by Coulomb's law, where these r's are the distance between the charge we care about and the charge that's giving that particular force. So, for example, the force on the charge we're looking at is equal to the force due to its interaction with charge 1, plus its force due to the interaction with charge 2, plus the force due to its interaction with charge 3, etc. Now, what are these funny things here with symbols? These are what we call unit vectors. These are vectors that go from the charge providing the force on the charge in question to the charge in question, but they have a magnitude of 1. So if you're not getting this stuff, it's okay. You can actually move on from this if you're not getting this. I'm simply giving commentary for people who care about this and who want to get some of the more technical detail. The way that you could actually write a unit vector would be actually just to draw a line going from the charge causing the force, or at least the origin charge, like in this case charge 1, directly to your charge. So let's say that your charge is 5 units to the right and 2 units down from charge 1. So your vector would be 5 times a unit vector to the right plus -2 times a unit vector going up. Well, we have names for those. Those are called I hat and j hat. The unit vector going to the right, in other words, the vector 1, 0, is often just called the vector I hat or I vector. It's also sometimes called X hat. It's also often called E1 vector, where E stands for ein, for just unit or 1. But anyway, it would be 5i minus 2j. Well, to make it a unit vector, you would need to divide by the magnitude of that vector that goes from charge 1 to our charge in my little example here. So what would the magnitude of that be? Well, that would be given by the Pythagorean theorem, which would be the square root of 5 squared plus -2 squared, all under the square root. That is called the square root of 29. So the unit vector going from charge 1 in my little example here to charge q would be, in the numerator, 5i minus 2j, all over the square root of 29. And then you would do the same thing for charge 2 and charge 3, etc. Well, this is not an AP physics class. This is not an honors physics class. So we're not actually going to deal with problems that deal with such things. Instead, I'm just going to mention them to you, and now we're going to move on. And we are nonetheless, though, going to think about force as a vector, but we're just going to work in one dimension. So let's say we have a charge here right in the middle, and it's experiencing a force due to the presence of 2 other charges, Q1 and Q2. Unfortunately, I was being very sloppy and I forgot to put bold signs on my force vectors, F1 vector and F2 vector. Naughty, naughty, but I should have done that, or I should have put vector arrows over them. So, in any case, the idea is that now that we know that force vector equals F1 vector plus F2 vector, we can look at the free body diagram and figure out what is the direction of each of these forces, and then Coulomb's law tells us the magnitude of each of these forces. So, first of all, I'm going to ask you a question. What must be the case in order for this free body diagram to be true, where this vector to the left indicates F1 and this vector to the right indicates F2? What must be true in order for this free body diagram to be true? So, I'll give you a couple seconds. You can pause the video if you want to think about it. So, the answer is that these charges, Q1 and Q2, must be opposite in sign to our pink charge. So if the pink charge is positive, then Q1 and Q2 are negative. If the pink charge is negative, then Q1 and Q2 must be positive. If that is not the case, then these will not be attractive forces. For example, if Q1 was positive and if our pink charge was positive and Q1 was also positive and Q2 was negative, then the force from charge 1 would be the same magnitude that we have right here. In other words, the arrow would have the same length, but it would be pointed toward the right, because like charges repel and opposite charges attract. And you can imagine similar situations if we made Q2 the same sign as our pink Q, but Q1 having the opposite sign. In that case, F2 would be flipped around. Or if Q1 and Q2 both had the same sign of charge as our pink charge, then F2 would be flipped to the left and F1 would be flipped toward the right. So our net force would have the same magnitude but opposite direction. So let's take a look at a nice example. Calculate the force on each of the charges in this diagram. In fact, this is one of the problems in one of the packets that you're going to get soon. So, how do we do that? Well, we look at these three charges. We notice that the charge on the left is positive, the charge in the middle is positive, and the charge on the right is negative. So that means that there's going to be a repulsive force between these two charges. There's going to be an attractive force between these two charges. And there's going to be an attractive force between these two charges. Well, we said to calculate the net force on each of the three charges. So what's the first thing we're going to do? We're going to calculate the net force on the charge on the left. Well, that means that when we're calculating the net force on the charge on the left as our first calculation, we don't need to worry about the forces, the force of interaction between the charge in the middle and the charge on the right. That does not bother us. All we care about, this is what the superposition principle is telling us, all we care about is the force of interaction between the charge on the left and the charge in the middle, and the force of interaction between the charge on the left and the charge on the far right. And if there were other charges here, then we would add in the forces of interaction between the charge on the left and each of those separately. But there would be absolutely no contribution from the interaction forces between the other charges of each other if they didn't directly relate to the charge on the left. So, what does that mean? That means that if we call the charge on the left Q1, if we call the charge on the middle Q2, and we call the charge on the right Q3, then we say that F1 vector, the force vector on charge 1, the charge on the left, is equal to the force vector on charge 1 due to charge 2, that is the charge in the middle, plus the force vector on charge 1 due to charge 3, that is due to the charge on the far right. Here's our free body diagram on that. By the way, notice a vector that you might have expected here that is missing. We do not have a gravitational force vector. Why? Because we don't know where this interaction is taking place. And even if we did, we've mentioned before that the electric force is much larger than the force of gravity. It's many, many orders of magnitude bigger than the force of gravity. So even if this happened around the surface of Earth, the gravitational force on these charges would play absolutely no role to speak of in this interaction. So in any case, we recognize that, going back to the picture, this is a repulsive force, so the force of on charge 1 due to charge 2 must be to the left. And the force on charge 1 due to charge 3, that's an attractive force. That force must be to the right. Notice that I have made F13, the magnitude of F13, a good bit shorter than the magnitude of F12. I don't know for sure that that's the case yet, but I guess that it's the case, because charge 3 is a lot farther away than charge 2. Now, if the magnitude of charge 3 was much bigger than the magnitude of charge 2, well, I'd probably want to do the calculation first, but here this is just to give me a sense of scale, give me an idea of things. It might turn out that I was wrong. That's okay. The free body diagram is to help us set up the equation. So now, going from vectors to scalars, that is magnitudes with plus or minus signs in front of them indicating the direction of the force. Well, F12 is to the left, so I put a minus sign in front of that magnitude. F13 is to the right, so I put a plus sign in front of that. Well, what are each of these magnitudes? They are given by Coulomb's law. So after writing down our givens, notice that I've converted everything into SI units. This milli, this lowercase m is milli. Milli is 10 to the minus 1. You know, like a millipede has about 1,000 legs. Technically, that's not true. Typically, they have like dozens to a few hundred. But in any case, we pretend that they have 1,000 legs. Well, micro, we were talking about how these distances, look at these distances, this is the symbol for micro. Micro is 10 to the minus 6th. So each of these is some number times 10 to the minus 6th meters. Notice that the distance between charge 1 and charge 3 is 7 micrometers, because we have 4 micrometers to here, and then another 3 micrometers to here. So overall, the distance from 1 to 3 is 7 micrometers. So now, here is where we plug in our Coulomb's laws. Again, I just copied this equation from the previous slide, that the force on charge 1 is equal to the force on 1 due to 2, but that's to the left, plus the force on 1 due to 3, and that is to the right. And now we are ready to plug in our numbers. Notice I factored out a magnitude of Q1. These absolute value signs that I put around my charges are so that I can plug in my charges themselves without having to worry about plus or minus signs. I just plug in the magnitude of each charge, and then I deal with the minus signs as signs in front that we got from our free body diagram. So notice that after plugging that in, I get a force of negative 4.68 times 10 to the 15 newtons. That is an absolutely gigantic force. But keep in mind, even 1,000th of a Coulomb is a huge amount of charge, especially when you're talking about distances on the order of micrometers. Now, you can do the same thing for the other two charges. This time I'm not going to include a free body diagram, but I'll just note that the force on charge 2 due to charge 1, that is F21, is to the right, and the force on charge, because these two repel each other, and the force on charge 2 due to charge 3 is also to the right, because these two attract each other. Notice in this case I was a bit sloppy with my vector notation. That's okay because this is not an honors or AP physics class, but if it was, I would want to be a bit more explicit. I would then call this F21 vector plus F23 vector, and then that would end up coming down to magnitudes because each of these forces points toward the right, but again I was being a bit sloppy here. So in any case, we do get plus signs for each of them because each of the forces points toward the right, and we have the same type of deal as before. I factored out a common term. I factored out a K. I factored out a Q2 because I don't want to have to plug in as many terms. Remember, the fewer things you plug into your calculator, the fewer mistakes you are likely to make. So now we plug in our numbers, and we get a force of plus 2.15 times 10 to the 16 newtons. So that plus sign indicates that the force is to the right, just as the minus sign that we got on our last force indicated that force was to the left. And finally, the force on charge 3 is due to the force on charge 3 due to charge 1, plus the force on charge 3 due to charge 2. But each of those forces is to the left, so again, if we're being sloppy and going directly from vectors to magnitudes with directions, we have negatives on each of these. And now you plug in magnitudes for the charges with the signs already being taken care of by our free body diagram that we didn't draw, but you should draw when verifying this. Factoring out common terms, and then plugging in numbers. Unfortunately, I screwed up the order of this animation, but this was the result of plugging in those numbers. So in this case, we have a negative force that indicating that the net force is to the left. So now, something that I want to draw your attention to is that if you add up all three individual forces, you did not need to do this. You were not told to do this in the problem. But just as a reality check, if you add up all three of these forces, it does turn out that you actually get 0 for the net force on the total system. Why? Well, Newton's third law tells us that the force due to the force on charge 1 due to charge 2 is equal to the negative of the force on charge 2 due to charge 1. The force on charge 2 due to charge 1 is equal to the negative of the force on charge 1 due to charge 2. The force on charge 3 due to charge 2 is the negative of the force on charge 2 due to charge 3, and you can again do that whole thing. Overall, you get 6 terms here, but each of those 6 terms has a negative term that cancels it out. Well, why should this be the case? The reason is that there is no external force acting on this system. Now, if we were told that all three of these charges were immersed in an electric field, then the net force would end up being positive because you would have a Coulomb's law force from what we would have just calculated, plus an F equals QE force from the electric field. But this was not immersed in an electric field. If it was, we would have been told so in the problem. So the net force on the thing is 0, which means that when you add up each of these three individual forces, you end up getting 0. Again, that's just a reality check. The net force on charge 1 is negative 4.68 times 10 to the 15 newtons. The net force on charge 2 is 2.15 times 10 to the 16 newtons with a positive sign, and the net force on charge 3 is negative 1.68 times 10 to the 16 newtons. So that's you would have these three as your individual answers with the proper signs. So if you had gone through all of the hard work of solving a problem like this, and you realized that the net force on everything didn't add up to 0, then you know that you've done something wrong. Now, that's not always apparent given particular directions. For example, you might have just been asked, oh, find the net force on charge 2. Well, the net force on charge 2 is actually positive. It's not 0. And if you're not asked to calculate the net force on charge 1 or charge 3 or both, then you wouldn't have any reason to have those numbers ready. But in this case, we did have those numbers ready, and we're able to check them and made sure that they were equal to 0. Equal to 0, that is, when we added them up. So now let's circle back to electric field. What is an electric field? How do we visualize electric fields? Well, we've already talked about how the electric field is the force per unit charge. In fact, you can actually get that force on a point charge because the force per unit charge, so just divide by the point charge, and we know Coulomb's law, so just, again, dividing that by that point charge cancels these Q's. So the force due to a point charge, or sorry, the electric field due to a point charge is just K times the point charge itself divided by the square of your distance from the center of that point charge. But how do we visualize electric fields? Well, this diagram right here could just as easily show you how to visualize a gravitational field around a spherically symmetric massive body. And indeed, that's exactly what it would represent if we weren't talking about electricity here. Well, in this case, this is a way of visualizing the electric field around a spherically symmetric, negatively charged body. So how would we know it's negatively charged? It's because the arrows are pointing inward. We're going to get to that soon. But long story short, electric field lines tell you or at least the direction on electric field lines tells you the direction that a small positive charge would feel if you were to immerse it in that electric field. So just imagine some electric field being created by a big distribution of charges randomly distributed around space, and you imagine putting a very small positive test charge there. What do we mean by small and test charge? What we mean is that the charge is so small that the field contribution from that particular charge is negligible compared with the electric field as a whole in which it is immersed. So imagine an apple falling from an apple tree, everybody's favorite since Isaac Newton, of course, we supposedly loved apples, but the mass of the apple is negligible compared with the 5.97 times 10 to the 24 kilograms of Earth's mass. In other words, the gravitational field created by that apple is so small that it does not really affect the gravitational field created by Earth. That's what we're talking about when we're dealing with a test charge. The electric field created by that test charge is so small that it does not really do anything to the overall electric field created by everything else. So if you put a test charge anywhere near a big distribution of negative charges, it's going to feel a force, well, toward that distribution of negative charges. And if it's a spherically symmetric distribution of negative charges, then that force is going to be directed toward the center. What about if you have other types of charges? Well, we need rules. So here's the idea. You imagine picking a point just anywhere, and imagine putting a very small positive charge there. If you were to calculate or determine the force on that point from all of the other charges in the universe, and you'd have both a magnitude and a direction on that, then you would just draw an arrow. If you wanted to denote a big force, you would draw a long arrow. If you wanted to denote a small force, you would draw a short arrow. The direction of the arrow should be the same as the direction of the force. So let's practice this on a few. There are also other rules. For example, field lines are never allowed to cross. So I'll give you a couple of seconds to pause the video and ask yourself why electric field lines can never cross. So If you've unpaused the video here, or didn't bother pausing in the first place, hopefully you knew the answer if you didn't pause in the first place. The reason that electric field lines can never cross is because well, among other reasons, the electric field is a conservative force field. Just like gravitational force, electric forces are conservative, meaning energy is going to be conserved in these types of interactions. It's not going to disappear anywhere due to just those types of interactions. It's not going to get absorbed into heat or anything like that. But if that's the case, that means that you always have a well-defined direction, a well-defined magnitude and a well-defined direction at any point in space. Why is that the case? Well, that's a subject of multivariable calculus, which we're not going to worry about. But long story short, anytime you have a conservative force field, the electric field direction is always going to be well defined. It's going to have a particular magnitude and a particular direction at any point in space. And if that's the case, you cannot have multiple magnitudes or directions at a particular point in space. You could think of it in terms of the function thing, how in kindergarten math you're told that something is only a function if it passes the vertical line test. I mean, I've never really liked that definition, but it's relevant for us here, because in this case, the idea is that if it fails the vertical line test, then you would have multiple possible values at any particular spot. Well, conservative vector fields do not act like that. They always have one particular value and one particular direction at any particular spot. Also, electric field lines must begin on positive charges and end at negative charges. You cannot end an electric field line at a positive charge. It's got to start at a positive charge, meaning that the direction of the arrow points away from the positive charge and the direction of the arrow points toward the negative charge. Here's an example of that. Here we have what we call an electric dipole. We have a positive charge up here and a negative charge down here, and we have a bunch of arrows that have been drawn, and the lines have been used to connect these arrows. Well, does this make sense? Let's say you put a little positive test charge right here. Well, it's going to be repelled by the positive charge here. It's going to be attracted by the negative charge. Everything is good. It's going to feel a strong attractive force downward in this direction. Well, that seems to match this. What about if you put a positive test charge, say, at this point right here? Well, that's going to feel a force down and to the right from the positive charge, and it's going to feel a force down and to the left from the negative charge. But it turns out, in this case, the overall force is down and to the right. Why? Because you're closer to the positive charge than you are to the negative charge in this example. If you want to be equidistant from the two, then that would be at a point right in the middle here. Well, at a point right in the middle, the rightward component from the positive charge ends up getting canceled by the leftward attractive component from the negative charge, and the only overall direction that doesn't get canceled is going to be the downward direction, which ends up getting added up. So another example of this right here is what I like to call a centipede diagram. In this case, we have two positive charges that are, well, they're repelling each other. So anywhere you put another positive test charge, you should expect that the net force on it is going to be away from this overall system. And indeed, that is what it is. But we said every field line must end on a negative charge. Well, where are the negative charges? Well, they are out of the picture. They are somewhere else in the universe. But I can guarantee that somewhere these electric field lines are ending on negative charges. They're just out of the field. So based on the distribution of this and the geometry, I've called this a centipede diagram after those little critters that you see skittering around on your basement walls at 50 miles per hour. So what about this situation? Here we have a cockroach diagram where we have a small positive charge coming out of here, going into a larger negative charge over here. What are the units on here? Well, we don't care. The point is that the magnitude of this negative charge is twice as big as the magnitude of this positive charge. Well, what do you see? That means that there must be twice as many electric field lines going into the negative charge as are coming out of the positive charge. Well, where are these other electric field lines coming from? They must be coming from other positive charges that are outside of the picture. So what if we have three charges, such as in this praying mantis diagram? Hopefully all of these analogies here aren't bugging you. Well, if so, maybe crawl away, I guess. But these diagrams were actually created in a lab that we did on this some time ago in one of my classes about 8 or 9 years ago. But in this case, notice that we have 12 field lines coming out of the +3 charge, 4 field lines going into the -1 charge, and 8 field lines going into the -2 charge. Well, that makes sense. The total charge that you see on the screen here is 0, which means that every field line that comes from positive must go into a negative. Now, also, the 12 here is 3 times as much as the 4 here, and the 4 here is half as much as the 8 over here, because the magnitude of the charge over here on the left is half as much as the magnitude of the charge over here on the right. Now, I definitely urge you to check out some of these apps. The PhET simulations for this are very good. There's a little electric hockey game here. There's also a charges and field simulation up here that you're strongly urged to play around with and get a good visualization for how electric fields work. So I know that this has been a more technical video than most of the ones that we've had so far in the videos for this non-AP, non-honors class, but nonetheless it's something that I expect that if you go back through it, if necessary, that you'll be able to understand. So if you have any questions, please let me know, and thank you.